Hi, and thanks for tuning in to our talk. Our result is titled Decremental APSP in Directed Graphs Against an Adaptive Adversary. My name is Viktor Hansen, and this is joint work with Jacob Evald, Maximilian, Probst, Gutenberg, and Christian Wulff-Nilsen. So in dynamic graph algorithms, we study dynamic graph problems where the graph G is subject to changes over time. And typically we wish to support some notion of a deletion and an insertion, while also supporting queries about the properties of the graph in its current version as it changes over time. When we support both deletions and insertions, we refer to this as the fully dynamic setting or fully dynamic graph problem, but we may also consider the cases in which we only allow for either. So we refer to the case in which insertions are only allowed as an incremental graph problem, respectively a decremental graph problem if deletions are only allowed. Or more generally, we refer to these problems as being partially dynamic. For gauging the quality of a partially dynamic algorithm, it is quite natural to consider the total running time. And that's the total time it takes to process an adversarial sequence of updates, starting from the input graph and ending up with either a minimal or maximal graph, depending on whether you're deleting or inserting elements. So since the performance of dynamic algorithms is measured in relation to an adversarial sequence of update, it's important to specify the type of adversary against which a performance guarantee of a dynamic algorithm holds. Unfortunately, a lot of algorithms assume a weak adversary, a so-called oblivious adversary, who must decide on the entire sequence of updates before the algorithm runs. And in other words, updates are independent of any random bits. And unfortunately, this also means that the provided guarantee does not necessarily hold against a stronger type of adversary, whose updates can be made on the go and where the choice of updates can depend on answers to queries or updated query latencies. So we refer to an adversary who can do this as an adaptive adversary. So you may ask, why is this important? And in many cases, it does indeed seem quite unnatural to specify the entire sequence of updates before the algorithm runs. So say you want to use your new fast dynamic algorithm as a black box in another algorithm. Well, then the guarantee which holds against the weaker type of adversary does not necessarily hold if the sequence of updates depend on answers to queries in the algorithm which uses your algorithm as the black box. And unfortunately, many guarantees provided for dynamic graph algorithms only hold against a weak or oblivious adversary. Finally, it should also be mentioned that the above definitions, or by the above definitions, a worst case guarantee provided for a deterministic algorithm will always hold against an adaptive adversary. So the problem we study is that of decremental APSP in unweighted directed graphs, and that is given an unweighted directed graph G. We wish to support edge deletions and support all paired shortest path distance queries. And the latter we will be doing in constant time, since we explicitly maintain the distance matrix D hat at all times. We also study the problem both in the exact and approximate setting, so given some parameter t greater than or equal to 1, we over-report the distance by at most a factor of t. So when t is equal to 1, the distances are made exact. Table 1 lists the state-of-the-art for exact APSP and unweighted graphs and our results. And the state-of-the-art until now was due to Botswana and others, and they described an oblivious Monte Carlo algorithm with n-cubed total running time up to polylogarithmic factors. And the suppression of polylogarithmic factors is indicated by the tilde above the big O, by the way. So if you look in the table, it actually lists adaptive in the entry of Botswana, and that is because their data structure is capable of reporting shortest paths, in which case the oblivious adversary assumption has to be made, but we may assume an adaptive adversary if we disallow for path reporting. Our first result matches their time bound, but it's an improvement in the sense that it's deterministic and hence not Monte Carlo, and this even holds against an adaptive adversary when we also allow for reporting of shortest paths. Prior to Botswana, the best decremental algorithms for decremental APSP and unweighted graphs was no better than running the decremental SSSP structure of even and Chilliwack from each vertex in the graph. And the data structure of even and Chilliwack, commonly referred to as an ES tree, runs in total time O of m times d and is capable of answering SSSP queries for vertices at distance at most d. So d is some distance threshold and m is the number of edges in the graph. So since the distance is at most n between any two vertices in an unweighted graph, the total running time becomes n times n, which is mn squared. For the approximate setting, Table 2 lists the state-of-the-art and our results. Baswana showed the exact data structure could be adapted to maintain APSP and weighted graphs in total running time square root of m n squared over epsilon. But unfortunately, the running time only holds against an oblivious adversary. Bernstein also presented a remarkable result with total running time m by n by using a clever approach of shortcutting paths. But unfortunately, this also suffers from this rather weak adversarial assumption. So our first approximate construction matches the bound of Baswana, and it's deterministic, and therefore it improves in the adversarial assumption. Furthermore, we may report paths in time proportional to the length of the path. We also provide another data structure with a better time bound, which holds with high probability and against an adaptive adversary. And that's the rather unpleasant looking bound you see in the second row of the table. We refer to the full version of our paper, which is available on arXiv for more comprehensive treatment of related work. So in order to get us started, I will provide a brief recap on the approach of Baswana and how our approach differs to theirs. And in their approach, they rely on a well-known hitting set theorem in which we sample hitting sets at various scales corresponding to different values assumed by I. So the hitting set h rho I is obtained by sampling each vertex independently with some constant probability such that the expected size is O of n over rho to the ith power. In the figure, those would be the vertices that have green crosses over them. So the reason this is helpful is that because with high probability for any vertex pair u and v for which the shortest path distance between u and v and g lies between rho to the power of I and rho to the power of I plus 1, there will be some sampled vertex from h rho I which intersects this path. And this invariant holds at any point in time once the sampling has been done. So let us now say that the distance from u to w or the distance from w to v increases. Well, then the distance from u to v may have increased. So what we do is scan the set of sampled vertices at the scale to see if there's another witness which retains the u to v distance. And otherwise we update the estimate. So if such a witness vertex exists, then it must have been sampled with high probability at least. So now there are a quadratic number of pairs, and we can cover all distances with a logarithmic number of distance scales. So each such pair may increase its value proportional to rho to the power of I plus 1 times before it needs to consider the next scale. And each time we have to scan the set of samples at the scale. But each time we move up the scale, there's a factor of rho fewer sampled vertices in expectation. So summing up, this gives us the desired time bound over all pairs of vertices. Now, if we recall, the problem with these types of approaches is that the sampling results in a Monte Carlo algorithm. And furthermore, the running time guarantees do not hold against an adaptive adversary in the approximate setting. So therefore, a natural solution would be to maintain the separator deterministically. And we do so by maintaining a small local separator for each vertex u at varying distance scales I. And then separators at level I will take care of the distances that fall within the corresponding scale. So to give an idea of our separator and the motivation hereof, we consider the following image which depicts u and its separator vertices at level I. And these are depicted in green. So here we fix the distance scale by setting d to be rho to the power of some I, where rho is some constant larger than 1 and I determines the distance scale we're considering. So say we wish to determine the distance from U to some other vertex V, and then since S is a separator, any U to V shortest path must intersect some witness W in S, minimizing this distance. This sort of hints at a recursive scheme in which distance changes on lower levels are propagated to higher levels. And therefore we ensure properties 1 and 2, and that is 1, if a vertex V is reachable from U in G minus Si of U, then V is close, or it must be close, in the sense specified, and otherwise it's far away. And second of all, as long as the U to V shortest path distance fall within the distance scale, there should be a witness W in the separator, for which it holds that the U to V and the V to W to V shortest path distances are at most D. So before describing the actual algorithm, let us briefly discuss some of the challenges in maintaining this separator dynamically. Namely, we need to keep the separator size sparse, and we also need to minimize the total running time of maintaining the separator. So if we briefly recall the picture from before, we can now consider what happens when G undergoes deletions over time. Well, the vertices move away from one another, and this means that invariants 1 and 2 of the separator algorithm may become violated. So how do we deal with vertices moving too far away? Well, assume that the distance from U to W exceeds D or is close to doing so. Then we perform 2 BFS searches in G, but only consider unmarked vertices in the search. The searches are made in parallel, one layer at a time, starting from U and W until a thin layer is encountered at either search. Furthermore, the layer must be at distance D or less. So all vertices of the sparse layer are now added to S, and the vertices visited during the search from W are now marked and never searched again. So since we require the separator set to be sparse, we will make use of a well-known result that shows the existence of such a sparse separator. So given an unweighted graph and two distances D1 and D2 that are sufficiently far apart, we can grow a BFS tree rooted at some vertex U such that we find a sparse layer L at distance between D1 and D2. And by sparse we mean small in proportion to the number of vertices closer to U than to L. This also means that when we sum up, this implies that the separator size becomes roughly N over D, and the running time becomes O of M, since a vertex is never searched again once it's marked. So let's turn our attention to the exact decremental data structure. We can handle small distances using ES trees up to distance C times log n in total time mn log n for all vertices, and we can easily afford that. But for larger distances, we need to describe a data structure di of u, which maintains a distance estimate di u, v, which is at least the true shortest path distance between u and v, and with equality if the distance falls within the range of I. So di of u maintains the separator Si of u throughout the entire execution, but we may also inductively assume that dj of u is maintained for all u where j is smaller than I, and that it's reported whenever distance grows past the current distance scale d, or rho to the power of I. So I tried providing an illustration here, and here the shortest path distance from u to v initially falls within the scale rho to the power of I minus 1 to rho to the power of I, but subsequently it exceeds rho to the power of I after updates. Upon receiving an update, the first thing di of u does is to restore the separator invariance in the manners described previously. Since the u to v distance exceeded the previous scale at level I minus 1, di of u initializes a priority queue, and it adds each element s of the current separator with key corresponding to the sum of shortest path distances from u to s and from s to v. And whenever a distance increase is reported by a data structure in the level below, the keys of the corresponding elements are increased suitably. And here's an illustration of separators and a hierarchy, which translates to how increased key operations propagate in the priority queues. So here the path u to v uses w as a witness of a 2-hop path, and the shortest path from w to v uses w prime as its witness. So what this means is that if the length of the shortest path w to v is increased by some amount delta, the distance estimates of all 2-hop paths that use w and v as a subpath are also increased by this same amount. As aforementioned, our construction maintains the distance matrix explicitly, and this can be achieved by maintaining a priority queue for each pair of vertices and maintaining the current smallest estimate at each level I, or infinity if the priority queue corresponding to that level has yet to be initialized. The entry of the distance matrix is the minimum element of the priority queue corresponding to that pair, and the correctness of such an approach can rather easily be verified. For the running time, the ES trees take mn log n total running time, and maintaining the separators take m by n time. There are n squared of the latter priority queues at log n levels, and each of these can increase at most n times, or increase their keys at most n times, yielding a total time of n cubed log squared of n. Again, this will be dominated by the cost of maintaining the priority queues of the local data structures. So for each vertex, maintaining the separator takes time O of m for a total time of O of m times n. The total number of elements in priority queues is n squared log n over rho to the power of I, and the number of increased key operations is rho to the power of I, and each of these operations take O of log n time due to the priority queue. This is a total time of O of n squared log squared of n, and over all vertices and distance scales, this becomes O of n cubed log cubed of n. And with that, I'd like to say thanks for listening. The approximate and randomized descriptions did not make this talk, but they do build on the same techniques presented here, so please go ahead and have a look at our paper if you're interested. And see you at iCelp. Bye.